Okay, so how is everyone today? Great? Good.
Stop it.
Now that so there's 6 sections of college algebra, and y'all are in section number 6. But there's 1, 2, 3, 4, 5. Now we finally got them all the sections resynchronized, because we diverged from the textbook to talk about intervals and natural domain, and all the different sections kind of like spread all out. But now we're back at the same spot. So now homework can resume. So then the WEXs will resume tonight. So, yay, that's good. Oh, you were thinking of a slightly different word than yay? Okay. Well. All right. So now we're in. Just to briefly mention, just to recap what we talked about last time. So today's the 12th. To briefly recap what we talked about last time, what is natural domain? What is that? What does that mean? Well, you have an expression, that's got multiplies, divides, and variables and square roots and what have you in it. And then that expression may not be defined for every possible value of x. So the natural domain is the largest set of x, say, if the variable is x. The largest set of x's so that the expression is defined. All right? So, for example, the expression 1 over x, so like this, 1 over x has natural domain what? Right. Anything at all except 0. You can't use 0. Okay, so writing that with equations, you could say it like this: x not equal to x not equal to 0. Drawing it as a number line, you could do it like this. Drawing it in interval notation like this. Okay, so all 3 of those, like that, and like that, they're all the same. And one slightly, possibly surprising matter about this is something like the following. I could say 2. How about 5 multiplied by w minus 3, and then all divided by w squared minus 10 w. But I had a 3 in my head when I was saying w, apparently. Minus 10w, and then, what am I thinking here? Plus 21. So there's an expression in w. And now, as a separate matter, but parallel, I'm going to ask, consider this expression over here. 5 over w minus 7. So these 2 expressions are similar. They're similar. This one is easier to deal with, okay, so I'll deal with it first. What is the natural domain of this expression? Right, anything but 7 is permitted. Okay, so you could plug in w is 10, you could plug in w is negative a million, you could plug in w is pi, but not 7. So you can't use 7, and you could draw that like this. You could say, anything but 7, or you could write it in interval notation like this. Anything but 7. All right. And then how about this one? How do we figure out the natural domain of this one? We factor it. All right. So factoring that, because in a real question it would say something like, here's an expression, find the natural domain of that expression, and also cancel if possible. Simplify it by cancellation if possible. So the numerator is factored already. And then, does the denominator factor?
Yes.
It does? Amazing. So, w minus 3 multiplied by what? Oh, wow. So do you observe that according to this factorization, there are some w's that cannot be permitted? Okay, what are they? 3 and 7 cannot be permitted. Okay, so as a result, so over here on the right, this is the natural domain, represented in the 3 ways. So therefore, the natural domain here would be anything but 3 or 7. So x not equal to 3, x not equal to 7. As a picture, you could draw it like this. Okay, and then as in interval notation, you could do it like this. Okay, but then now here's the rub, is that concerning this expression right here and that one, because these two are equivalent, can you perform a cancellation? You can, and then now. So we're going to make a cancellation. And when you do that, what do you get? 5 over w minus 7. So then making these two parallel considerations, I have a question for you. Is it the case, well, I'll write it like this. 5 times w minus 3 over w squared minus 10w plus 21. Okay, so in the first place, I'll write this. I'm going to write two equations. So this is a question. Are these in fact equivalent? Is that one the same as that one? Yes. They are. Now the reason why they're the same is because in the first place they have the same domains. Right? The w's that this one can use is the same as the w's that that one can use. Furthermore, whatever w you select, say maybe you choose w as 10, and you plug it in on this side. And then you calculate that and put that aside, and then plug in w as 10 and calculate it there and do it there, and then put that aside. Those two values would be the same. So these two are equivalent because their domains are the same, and furthermore, when you plug something in, the result is the same. That's what makes them the same. But as a separate question, is it therefore the case that this is equal to this? Are those the same? They are not. They're not the same. Why are they not the same? Right. Because considering this one in isolation, just all by itself, is it possible to plug in w as 3? It is. What about that one? It is not. Because their natural domains are not the same, these two are not the same. They're not the same. So in order to make this right, when you make such a cancellation in this class, the thing that gives you permission to do it and receive credit for doing it is that when you make such a cancellation, you have to say for W not equal to 3. That's when they are the same. Because in fact, these two expressions are the same for every W except 3. So they're the same for 3.1. They're the same for 3.1 million. They're the same for -8. They even have the same behavior at 7, right? Because they're both undefined there. So the permission to perform cancellation is you saying for W not equal to 3. Any questions about this idea? All right. So now let's move on to the next thing. So we're in section 2.1. It's called something like a rectangular coordinate system. So to begin with, we're going to talk about R1. So specifically, what I mean is that you know how when you write like an X, just an X all by itself, if you can imagine, you just write an X there. Maybe not. I'll just even just write it. Okay, I wrote an X there. What is its exponent? 1, right? So you don't write the 1 because it's usually implied. Okay, it's just implied. So what I'm saying is that by analogy, this is R1 because there's one of them. So it's like a single exponent. The way that you draw this is with a as a line. Now, from this point on, so I'm aware that the textbook and quite possibly any previous math teacher where they've talked about the number line, they put an arrow going the other direction. But from now on, I will not do that. Now, there's a reason why I won't do that, and now I need to explain that because it's making a break between what might be your previous experience. So concerning, suppose that we select two numbers, A and B. Then now, because I haven't drawn a scale, you know, like little marks and stuff, you can't really like tell me the values of A and B, but you can tell me which one is the greater. B is greater. Now, why is B greater?
It's to the right of it.
Okay, what's special about rightness? You know, to the rightedness. Why that? Now, which one's greater?
How do you pronounce upside down A?
B is that one is still greater because of the arrow. The arrow is the thing that signifies the direction of increase. It's that. So what I mean to say is that if you draw this or this or this, and you select 2 points and say, you know, call it A and B. A and B. A and B. Then, you know, if I say concerning that one, which one is greater, A or B? The answer is B. If I ask you that one, which one is greater? A is greater. And here's the problem. Which one is greater? Well, I mean, it's ambiguous. What could possibly be meant by this? Okay, now I appreciate that you know your previous instructors might have written the double arrow thingy, and I won't even you know I won't be upset with you if you do that because that's not really too much of a thing in our class. But you need to understand that I will not anymore, because we finally made it to this place in the class. Now, for those of you that really want a pointy bit on both sides of the thing, you know, it might disturb you a little bit that that one has you know its decoration, but that one doesn't. So this typical decoration on this side is like this. Now, that means that it continues going that way, but let's not forget that the increasing direction is that way. Okay, so it's just the same as that arrow those hooks, but flipped, just like that. Okay? You don't have to draw that if you don't like it. So concerning these, you can tell that B is the greater because that arrow is pointing to the right. Can you tell the SIGN of these? Meaning negative or positive. Is it possible to tell?
No.
It is not. Not currently. And I say SIGN because there's a math word SINE, sign, as in trigonometry. So I always say SIGN for positive and negative. So if I mark this right here, if I say there's a point and that's 0, okay, now can you tell me the signs of them? Right, they're both negative now. It's clear that that is the case. But if I picked up this 0 and I put it in between the A and the B, that'd mean that A is negative and B is positive. And then if I put it all the way to the left, then they'd both be positive. Good. So, all right. Now we have this concept of signed distance. So now, to be clear, when you're out on the street, you know, talking to folks about distances and things like that, they almost never does a person in normal conversation mean this thing that I'm writing. Rather they mean something that we're going to refer to as unsigned distance. Okay, so then, you know, if you round a little bit, we're in Dallas. You know, if you round a little bit, and then there's a big city to the south of here, Houston. Okay, and they're both on the same highway, 45. So, and just to make the numbers nice and round, I'll say that Dallas and Houston are exactly 200 miles apart. Okay, this is not true, but okay. So, signed distance would be saying something like this: the distance from Houston to Dallas is 200, and therefore the distance from Dallas to Houston is negative 200. That's what signed distance would mean. That's why I'm saying that that's not what regular folks are talking about. Okay. So signed distance. So signed distance from A to B. The formula for this is B minus A. Now again, going to and the reason why it's from B to A is that, well, it says from B to A, and that is the reason why B is first. And then you're subtracting A. So again, Dallas and Houston are cities. Suppose that it's the case that on Highway 45, which really does go through both towns, cities or whatever. Suppose that the very middle of Houston is at mile marker 150. I have no idea if that's even close to correct, but suppose. And then suppose further that the mile marker right in dead center of Dallas is mile marker 350. So the marker is 150 in Houston and 350 in Dallas. Then the distance from Houston to Dallas would be what? 200. It'd be 350 minus 150. So it would be, 200. Doing the subtraction in the other order, 150 minus 350 is what? Negative 200. Now, under normal circumstances, you wouldn't say, you don't say it's negative 200 miles. But it can be kind of useful to say that, because that might signify to you that when you say negative 200 miles, that might mean it's 200 miles traveling south, okay, instead of north. Okay, signed distance from A to B is thus signed distance from B to A. Then what's that? It'd be A minus B. And again, to make the city analogy, you could do this. You could say, well, here's a mile marker 150. And here's mile marker 350. So there they are. Now, if we wanted to travel from 150 to 350, then what I want you to see is that you could imagine it that you sort of put your pencil or whatever there, and then you draw that way. So I'll draw it above so that you can see what I'm drawing. So I draw that way. And now, how can I remember, because the way I've drawn it right now, I've already forgotten which way my pen was going. I forgot. Not really. I'll put an arrow here to remind myself that that means that I was drawing that way, right? From this one to that one. Okay? And what I'm telling you is that this thing right here, it is called 200. That's what it is. From that one to that one. Okay? And the way that you calculate it is the value that's at the pointy bit, that one, and then subtract the value that's at the other side. Whereas, if you start here and travel to the other one, then you travel like that, and then I'll put the arrow pointing that way so that anyone else who cares to ask, they can know, oh, it was from that one to that one. So now, if you get out your ruler and just measure both of those, they both measure, according to the ruler, as 200. Yet, one of these we're going to refer to as, one of these two, we're going to refer to as the positive one, and the other one is the negative one. Now, which one is going to be the positive and why? The top one's going to be the positive one, I agree, but why? According to the picture. Right. So look, this top one is pointing that away, and the world also points that away. So they're in agreement with each other. Okay? That is positive. And notice that this arrow is pointed in the opposite sense of the world. Okay, so this one is the negative one. All right. So, again, to go with a physical analogy, you could, you could consider this to be like a river, flowing water. The positive sense of the river is if you're swimming in it and going with the water. The negative sense is swimming in the river yet going against. Right? With the water, against. Okay? So now, most of the time when you ask when you're talking about distance on the street, you don't mean signed distance, rather you mean unsigned distance. And because that is so often the case, unsigned distance from A to B. Because you typically always do that, this adjective is usually left off, so you just don't even say it. So you don't say unsigned distance, you just say distance. Okay, so now how do you calculate it then? Okay, so like if I do B minus A like that, would that be right in all cases? So what we want is something where if we say that the distance from Houston to Dallas is 200, then the same response, the distance from Dallas to Houston, should also be 200. You see what I mean? So this couldn't be right. We've got to modify it somehow. Absolute value. That's how you fix it. But for reasons that'll become clear a little bit later, what I want you to observe is you could kind of think of it like this. So imagine that you've got two values, A and B, and here I want you to notice that this one on the top is 350 minus 200. 150 minus 150, and the one on the bottom is 150 minus 350. Right? The same two numbers, but just subtracted in the opposite order. So concerning this this A minus B, this A and B, it might be the case that in that order it's negative, but in the other order it's positive. So we're going to get to absolute value in the following kind of way. Suppose that we just take this A minus B which might be negative or positive, not sure yet. And at any rate, what if we square it? Right? Then the result will surely be positive, right? Because if it happens to be positive, we'll square that, and then it'll still be positive. But if it were negative, we square it, and then now it's positive, right? Because the squaring makes it go away. But that couldn't possibly be the distance, right? Because you don't square stuff. So how can we like more or less undo the squaringness that we used to make sure it was positive? Square root. So it may come as a surprise to you, maybe not, that in fact this is the definition of absolute value. It's not just that when you do that you happen to get absolute value, like coincidentally. This is what it is, and that's the reason why I keep harping on things like, well, what if you compute the square root of say z squared? Then what is this? Is it z? It's the absolute value of z. It's the absolute value of z, not just z. All right, good. So this is things about the reals are just are like that. Any questions about it? All right. So fine. So now, to get to slightly. Oh yeah, I do want to say one thing. Is that part of the reason why this convention right here, the double-sided one, works, is because why it doesn't end up causing too much trouble until you get to like maybe like a university level class, is that essentially uniformly in the whole world, something like 90% of everyone is born right-handed, like with a preference for the right hand. But understand that also means that 10% of people are left-handed. And those aren't exact figures, but it's close. But as a result, the world does have a bias towards right-handed people. It just does. Like you go buy scissors. It only makes sense if you're manufacturing scissors to make 90% of all your scissors right-handed. It doesn't make any sense to do anything else. But that also means that when left-handed folks go to the store, they might not be able to find scissors. Okay, we've got maybe a left-hander there. Okay, so the reason. Oh, sorry, I ranted and then forgot what I was saying. Is that the direction increasingness is to the right in the end for no specific reason other than essentially most people are right-handed. That's the only reason. So continuing that remark, now we're going to consider R, but instead of R1, we're going to write R2. And I would like for you to interpret that as meaning there's two copies of R. We've got one and then another one. So when you draw them, the way you draw it is, well, you've still got a horizontal copy, just like in the R1 case. So you still got that. And I'll call this one the first axis, because we've got or the first number line if you like. And we're going to have a second one. And the way we're going to do it is that right here we're going to mark and say that right there is 0. So that's the 0, and I've purposefully made it kind of tilted a little bit. That's the 0 of this axis. And so now I'm going to copy and paste it. I'm going to copy and grab so I have another one, and then I'm going to twist it so that it's at a right angle to this one. And because this one has a 0 and the new one I made is copied that one, the new one has a 0, and I'm going to make it to where the zeros are exactly on top of each other. So what I mean is that now there are two axes. They are at right angles to each other, and their zeros occur at that crossing. Now I've left something off that's important. The arrow, right? The arrow. So at the present time, concerning the vertical axis, it's not clear what direction is the direction of increase. So in essentially all cases, in math, the direction of increase is up. But you should be wary because in computer science, the increasing, where the vertical direction is concerned, the increasing direction is down. It's not up. The reason why is that you know, this screen is just like pixels, you know, and then TV screens used to actually not be this way. Like this is actually a very bright light shining through an LCD, and more or less these LCD pixels, the action occurs to them simultaneously. But once upon a time, back when the dinosaurs were roaming or whatever, and people had the TVs, an electron beam actually shot little parts of the screen and caused little bits of stuff to glow, because you're shooting energy at it, causes it to glow, and all the pixels are illuminated in order. And the order that it goes is it first does the one up here, and then it moves one over, and it shoots that one lights up, it shoots the next one, that one lights up, shoots that one lights up. And so this beam is going, lights those all up, and then it goes back to the beginning of the next row. So it moves down one, and then jumps over, and then down. So what's happening is that in time, the pixels are enumerated like this. Blop, 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 down. Blop, 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 blop. So as time is going, the beam's going down. And as a result, in computer science, the direction is down. All right, so keep that in mind. Fine. So just like in the one-dimensional case, so if you were right here, if you were standing on that point and you had to stay on that world, and it was not permitted that you could leave the graphite color, right? You can't go up or down or whatever. You're just there. You can either move with the world or against. And so that's just one possible direction of travel, either with or against. So this is a one-dimensional thing. Now this space, you know, the way to interpret it is that you could be out here, in fact. Okay, because it's not, you don't have to be on that axis or on that axis. In fact, what I'm talking about is there's a plane that's all of this stuff. So it's the whole thing. So, you know, you could travel with the, you know, in the direction of the first axis or against it. So that's one dimension in which you could travel. And you could also travel with the dimension of the second axis or against it. So this is two-dimensional. So this is the second axis. Okay, and just like this one-dimensional world has little one-dimensional creatures, these arrows, they can either be going with or against the world. This two-dimensional world has little two-dimensional creatures, and instead of being represented by arrows, they're actually represented by swirls. Okay, so the swirl looks like, not squirrels, swirls, like mixing, you know. So the way that it works is that this is the first axis and this one the second. So the way that you make a positive swirl is that you swirl first following the first axis and then turn to follow the second axis and then come back round. So what I mean is that, okay, I'll follow the first axis for a little bit, and now I'll follow the second axis, and I'll come back round. That's what positive looks like. Now, the way that you can always surely remember this is because if you have an axis on your page, please take your right hand, not your left, and put it on the page, and stick your thumb up. And now notice that your fingers swirl in that direction. And it will not work with your left hand. Okay, so this is another example of the right-handed convention. Okay, but in 2D. So you know, it doesn't. Your left hand won't do it. And then you know you can imagine that we would get even a third axis, and then you know you can imagine just taking this and you know I could hold it sideways and then pierce another axis through it so that it's coming out. But then you'd have to decide, okay, which way should be the pointy way, you know, where should you put the arrow? Again, there's a way to reckon it so that it's right-handed. And you have to deal with this in physics and all kinds of stuff. You know, so there's the, you know, when you're doing electricity and torque and what have you, there's something called the right-handed rule. And in chemistry, if you go there, organic chemistry, molecules come in right-handed versions and left-handed versions. Except they don't call it that. They've got their own fancy name called chirality. Okay, but at any rate, it makes for some funny situations. Like imagine, you know, if you can imagine. Well, notice that my right hand, if you imagine this to be a mirror, then it would reflect to my left hand. Or if you like, imagine in your mind's eye, holding up your hand, standing in front of a mirror, like in the bathroom, hold up your right hand, and the person in the mirror, what hand are they holding up? Their left hand. So when you make that reflection, that's what occurs. So if you take the molecule that is lemon smell, you know, like the smell of a lemon, and then you reflect it across a mirror, it's another molecule. But it doesn't smell like lemon. What does it smell like? That's a good guess. Lime, it's not. It's a good guess, but it's not. So if you reflect limonene, the right-handed lemon smell, limonene, and get the left-handed one, it's pine. Yeah. So like, you know, the joke, the organic chemistry joke is, you know, you could an organic chemist, you know, and they're drinking lemonade, but in the mirror they're drinking pine sol. You know. Okay. It's terrible. All right. So these things are important. Good. So now to come up with this, a naming system, we want to name this point. So just like on this this axis right here, you know, we name that point 350. That's its name. We want to be able to name points out here. So the way that they get named is by projecting them onto the horizontal and vertical axes, or if you like, the first and second axes. And I'll say it like this. Imagine that this is a flashlight here, very bright, very far away. Then that red point would cast a shadow on the horizontal axis. And its shadow would look like this, and this is a right angle. Okay, now we have a point that's on the first axis, so now we can ignore everything else and consider a one-dimensional problem and just measure it on the first axis. Suppose that we measure it to be A. So it's that value on the horizontal axis is A. Then we can do exactly the same thing, but onto the vertical axis. So shine a flashlight, very far away, cast a shadow, looks like this. Okay, and suppose that we measure that to be B. So now this shape right here, right, this thing, of course, what's its name? That's a rectangle. Now that's, I mean, that obviously, right? But that's the reason why this is called a rectangular coordinate system. That's the reason for that name, is that every point is on the corner of a rectangle. As a result, in order to say the full name of that point, you need two numbers, A and B. So they're going to be written like this. One number is going to be written there, and one number is going to be written there. So which one gets written where? A's first, why? Because it's on the first axis. And B is second because it's on the second axis. And if there were 18 more axes, then they'd be in that order. Now, I heard y'all say it, but I hope that you've noticed that I've scrupulously not said the x-axis. I've been very careful not to say such a thing. But I will admit that we're going to start dealing with problems that have two variables in them. Like that's as opposed to something like this. So like this was a problem that had just one variable, x, in it. And here's another one where we just had one variable, w. We're going to start dealing with problems that have two variables. And we're going to need two axes. And it is very often the case that those variables are x and y. And in that case, it is essentially always the case that this one is x, reckoned as x, and this one as y. But don't get too emotionally attached to x and y, because it could just as well be w and p. There's nothing sacred about those names. Okay, good. Next, I have a question. Suppose that we have this equation that has two variables in it. Okay? And then I could ask, is the point, and this is again with the convention that x represents the first variable and y the second variable. Is the point 3, 2 part of, and this part of is kind of loose. We're going to make this better on Friday. Part of this. What I mean to say is that could you plug in that point into that equation, and does that are we going to get a yes? Okay, so let me explain. So specifically, I want you to plug in xy equal 3, 2, meaning that everywhere you see x replaced with 3, and everywhere you see y replaced with 2. So it would read 2 is equal to 2 multiplied by 3 minus 1. And now we want to simplify both sides. So the left-hand side simplifies to 2, and the right-hand side, 5. So now I have a question that you are very likely to say the wrong thing. Is this an equation? Yes, it is. And I'm not, I haven't made an error. It is an equation. But if you're confused or disturbed by that, then let me show you what the problem is. All an equation is it's a thing that it's two expressions, one called the left-hand side, the other the right-hand side, and an equal in the middle. An equation evaluates to a logical value, which is to say true or false. So is this an equation? Yes. What does it evaluate to? False. So if you look at this and you say that's not an equation, what you heard me say is you thought I asked, is this an equation that evaluates to true? In that case, the answer is no. Okay, so finally, I know that we're against the clock, but I have to say this last thing. So is how about 4, 7 part of it? So in this case, yeah, we replace the 7 like that, and then 2 times 4, and then subtract 1. The left-hand side becomes 7, the right-hand side becomes 7. Is this an equation? It is. Is it true? It is. So, yes, equation that evaluates to false. Equation that evaluates to true. All right, have a nice Wednesday.